The Boomerang Nebula is colder than the blackness of deep space. It's the coldest natural place astronomers have found, at around 1 degree above absolute zero. That immediately tells you something surprising. Cold in space isn't just freezing, it's extreme and unintuitive. Define cold here as low thermal energy in matter, not just a subjective feeling. You should care because those conditions test physics we build machines around. Mechanism follows briefly. Low temperatures occur when gas expands rapidly, losing internal energy, or when radiation drains heat away over long time. In the Boomerang Nebula, the gas expands fast after a stellar outburst, and so it cools dramatically. For a concrete example, the nebula's gas drops to about 1 Kelvin, colder than the cosmic microwave background. Quick mental image: imagine a cosmic fog that froze by expansion alone. Anchor this. The universe hides places, naturally colder than any Earth lab except special setups. Cold in space means very low thermal motion of particles, not empty silence. That definition matters because temperature measures particle energy directly. You should care because low temperatures change chemistry and physics dramatically. Mechanism is simple to state. Temperature reflects how fast atoms and molecules jiggle. When those motions slow, quantum effects and unusual phases can appear. In interstellar space, the main cooling mechanisms are expansion and radiative losses. Gas expands after stellar pulses, so it does work and loses internal energy, and radiation carries energy away slowly over millions of years. For a concrete example, molecular hydrogen in a dark cloud moves only a few hundred meters per second at 10 Kelvin, versus kilometers per second at thousands of Kelvin. Another example comes from dust grains, which emit infrared photons, letting gas cool further in shielded regions. One sentence recap: cold means low particle energy, and that changes how matter behaves fundamentally. The Boomerang Nebula sits about 5,000 light-years away, and it surprised astronomers. Define it simply as a protoplanetary nebula with extreme outflow speeds. You should care because it shows nature can reach near absolute zero temperatures. Mechanism is striking yet straightforward. A dying star ejected a dense shell of gas very quickly, and that shell expanded supersonically. As it expanded, the gas did work and cooled to nearly 1 Kelvin. Observations with millimeter telescopes measured the gas's low thermal emission, confirming the chill. For a concrete example, the co-molecules emission lines in this nebula are unusually faint, consistent with very low excitation temperatures around 1 Kelvin. Another real-world contrast: Earth's liquid helium baths sit near 1 Kelvin too, but the nebula achieves that naturally across light years. Anchor: the Boomerang Nebula proves astrophysical dynamics can produce temperatures colder than many human-made systems. Paradoxically, some Earth labs reach temperatures lower than many cosmic places. Define these labs as systems that isolate matter and remove thermal energy. You should care because laboratory cold unlocks new physics and quantum technologies. Mechanism relies on staged cooling and clever traps. Engineers use dilution refrigerators, adiabatic demagnetization, and laser cooling to strip energy from particles. Each stage lowers temperature by orders of magnitude, and combined systems can approach nanokelvin scales. For a concrete example, Bose-Einstein condensates form at 100 nanokelvin temperatures, where atoms behave as a single quantum wave. Another example is superconducting qubits, which operate near 20 millikelvin inside dilution fridges. One sentence recap: Earth labs achieve colder temperatures than most natural cosmic spots by forcing isolation and engineered cooling paths. The cosmic microwave background sets a universal temperature floor for the universe. Define it as relic radiation from the Big Bang, now at 2.725 Kelvin. You should care because this background defines the ambient radiation every object experiences. Mechanism is cosmological expansion, redshifting energetic photons to microwave frequencies, lowering their effective temperature. Over 13 billion years, that radiation cooled from thousands of Kelvin to just under 3 Kelvin today. For a concrete example, any dust grain in intergalactic space will eventually equilibrate near this background temperature, unless additional heating occurs. Another concrete case: the Boomerang Nebula is colder than this background, which is remarkable because usually the background fixes the minimum. Anchor: the cosmic microwave background is a pervasive, measurable temperature that shapes low-temperature astrophysics. Many solar system bodies host extremely cold surfaces, often near dozens of Kelvin. Define these as worlds with thin atmospheres and weak sunlight, where heat cannot accumulate effectively. You should care because cold surfaces preserve ices and organic molecules for geological time. Mechanism depends on distance from the sun, surface composition, and insulating layers. Far from the sun, solar flux is tiny, and surfaces radiate heat away to space. If an object has no atmosphere, heat cannot be retained overnight, and shadows become ultra-cold. For a concrete example, Pluto's night side can drop below 40 Kelvin, freezing exotic ices like nitrogen solidly. Another example is Jupiter's moon Europa, where surface temperatures fall near 50 to 60 Kelvin in shaded regions, preserving water ice. One sentence recap: distant small worlds are frigid laboratories for preserved ices and slow chemistry. Interstellar molecular clouds are among the coldest places that actually form stars. Define them as dense regions of gas and dust shielded from starlight, with typical temperatures near 10 Kelvin. You should care because these cold conditions enable molecules and complex chemistry to form. Mechanism mixes shielding, low densities, and radiative cooling. Dust shields ultraviolet light, and molecules radiate energy in millimeter and infrared lines, letting the gas cool. Gravity then can slowly gather cold, dense pockets toward collapse and star birth. For a concrete example, the Taurus molecular cloud shows dense cores at 8 to 10 Kelvin, where protostars emerge. Another real case, CO and ammonia lines map those cold cores, and telescopes reveal chemistry that only occurs at low temperatures. Anchor, molecular clouds are nature's refrigerators and star nurseries at the same time. Some of the coldest physics is exotic and paradoxical, near neutron stars and inside quantum fluids. Define these regimes as places where thermal energy is low relative to quantum binding energies. You should care because they force new physics and surprising states of matter. Mechanism can be counterintuitive. Neutron stars have crusts where individual ions are locked in a lattice at low thermal motion, while interior regions may host superfluids and superconductors despite high overall energy density. Quantum fluids on Earth, like helium-3 at millikelvin temperatures, flow without viscosity and reveal macroscopic quantum phenomena. For a concrete example, neutron star crust temperatures can be millions of Kelvin internally, but surface layers cool to comparatively low effective temperatures, letting unusual solid phases form. Another concrete example, laboratory superfluids reach microkelvin ranges and exhibit vortex quantization observable in experiments. One sentence recap: exotic cold mixes low thermal motion with quantum coherence, producing surprising phases. The takeaway is simple: natural and human-made cold differ strongly, and each teaches us physics. The Boomerang Nebula shows nature can beat the cosmic microwave background locally. Laboratory systems go colder still to probe quantum behavior and develop new technology. If one idea stays, remember this: temperature measures particle motion, and when motion stops, new physics appears. If you enjoyed this, please consider watching another exploration of extreme astrophysical phenomena, and subscribe gently if you want more.